Hello, ma'am. Can you hear me and see my slide? Can you just confirm in chat box that you are seeing my slide and I'm audible to you? Ma'am, can you just confirm that am I audible and you can see my slide? Hello? Okay, let's start. So, okay, good evening everyone and welcome to the problem solving session for the course Coordination Chemistry, which is taken by Professor Devasisri from IT Kharagpur. And myself, Satya Prakash Yadav, a PMRF scholar from August 2020 batch, and I'm working with Professor Satish Patil from SSU Department, Indian Institute of Science, Bangalore. So first, I will briefly explain you about what we have covered and what we are going to cover. So so in the big one, basically we introduce you people to the coordination complexes, and we have solved the problem based on that, and we classified the ligand into three types. And in week two, we basically discuss in detail the nomenclature of the coordination complexes. In week three, basically we discuss about the coordination number and the geometry. So we started with coordination number 3 and we went up to coordination number 12. And what are the geometry possible for each of the coordination number we have discussed. In week 4, basically we discussed about the structure, uh, uh, structures, symmetry isomerism and coordination equivalent. So in isomerism, basically we discussed about the structural isomerism and stereoisomerism. In stereoisomerism, we discussed about the uh, two different kind of isomers, diastereomer and stereoisomerism, and little bit about the coordination complexes. In week 5, we have discussed about the different kind of bonding in complexes. Basically, what are the bonding theory proposed for the complexes? So, valence bond theory, and we discussed why it called valence bond theory, and other one is crystal field theory. And in week 6, we saw the what is John Taylor distortion, why John Taylor distortion occur, and what is the effect of John Taylor, and little bit about the spin cusp. In week 7, we discussed the detail in about the color and optical spectra of the coordination complexes. We discussed through the crystal field theory. And in week 8, basically, we discussed about the Argel and Tanabe-Sugano diagram. So here, basically, we take the help of crystal field theory and see like we try to assign the what are the peaks appear in the optical spectra, and we try to assign through the Argel diagram and Tanabe-Sugano diagram. So Argel diagram is just it's a qualitative and applicable for weak field ligand, while Tanabe-Sugano diagram is for the strong field ligand complexes. In week 9, we basically discussed about the crystal field theory. What is the application of crystal field theory? How we discuss the hydration of the 3D metals in +2 oxidation state, and we discuss how the size ionic radii changes for the high spin and low spin complexes, and we discuss in different detail about the spinels. In week 10, basically we what we are going to discuss. I will just reference the in lecture 30, Professor had discussed about the magnetic measurement, So I will just little bit give the introduction about the magnetic measurement what he has taken in the Big Ten, and then in lecture 31 he little bit discuss about the magnetic measurement, and after that he discuss about the ligand field theory, and in lecture 32 he discuss about the sigma orbitals. So let me flip my computer and I will discuss each and every point. Okay, so this is basically like if we have titanium in 3 plus, vanadium 4 plus, and chromium 3 plus, magnesium 3 plus, and iron 3 plus, and if it is in the like high spin complex, how many number of unpaired electron they are having? Like suppose titanium is D1, so it has one electron. Vanadium 3 plus is D2, it has two unpaired electron, so it's D2G2, and chromium it has D3, so it has uh, uh, T2G3, 3 unpaired electron, where magnesium 3 plus is D4, so it has T2G3 and Eg1, so it has 4 unpaired electron, and iron 3 plus is D5, it is T2G3 and Eg2. So these are the like 5 unpaired electrons. I can just draw through the crystal field theory. So 1, 2, 3, 4, 5 like this. So basically if we consider for titanium, this is only one electron. For vanadium 3 plus it is two electron, and for chromium 3 plus and like that. So if they have n is 1, 2, 3, 4, 5, s will be the half 1, 3 by 2, 2, 5 by 2. And if we calculate what is the magnetic moment, so it will be like square root of n plus 2. So basically if we consider for n is equal to 1 it will be 1.73, n is equal to 2 it will be 2.83, and n is equal to 3 it will be 3.87, and n is equal to 4 it will be 4.9, and n is equal to 5 it will be 5.92. But experimentally observe what is the magnetic moment. It is not exactly what we are getting, but it will be somewhat there, 1.7 to 1.8. Those contribution I will little bit discuss in detail from where it is coming. Okay. So next thing, like professor has immediately, like in this he started from the what is the diamagnetic, paramagnetic, and ferromagnetic and antiferromagnetic. So I will just make a table and explain it about the this curve, how it is varying for the susceptibility versus temperature plot. So first of all, I will write about the type. What are the different types of magnetic bodies are there? Types. So I will just give the heading the types of. 1 minute. It is giving this problem. Types of magnetic bodies. So in first column it is type. In second column it is caused by, from where it is coming. Third column is magnitude of chi g, and what is the, sorry, it is, then their temperature and magnetic field dependence, and then finally we give the example. So if we are discussing about the diamagnetic, so what is the cause by? So there basically we have paired field cell electrons. Okay, and the effect is submerged by the unpaired electrons. So their magnitude of chi is basically negative n small, negative n small, in order of minus 1 into 10 to the power minus 6 CGS unit. Now, what is the temperature and magnetic field independence? So they are independent of T and H. What are the example like water, KCl? These are the like uh, diamagnetic material where we have the paired and filled cell electrons. Coming to the paramagnetic. So paramagnetic basically from where that paramagnetism come due to the unpaired electron. Unpaired electron spins in orbital motion. So what is the magnitude of chi value? They are positive and they will be in the order of 10 to 100 into 10 to the power minus 6 CGS unit. So now, like how it will vary like with temperature. So they are first independent of independent of H, but their um, chi value is inversely proportional to 1 by T. So example are like you can take any complex like a low spin complex, like suppose I take chromium H2O6 SO4. So this is a paramagnetic substance. Now coming to the ferromagnetic substances. Ferromagnetic substances. So what are their characteristics? They are like paramagnetic, but the thing is that here like they have unpaired electron, but they are neighboring particle. The right word is neighboring particles with unpaired electron, unpaired electron, paired electron spins interacting among themselves. That is the important thing. So what happens? They in the presence of magnetic field, they align all in one direction, and their chi value is positive and very large. That is the uh, important thing to consider. So if I take the value 10 to the power minus 2 to 10 to the power 4 into 10 to the power minus 6 CGS unit, right? So if I discuss like how chi-t varies, so above TC, I will come. What is the TC? Above TC, chi-g is inversely proportional to T, but below TC, chi-g rises abruptly. Okay, so examples are metallic 3D metals like metallic iron. The last one is antiferromagnetic. Antiferromagnetic. So here what happens? Like here also like neighboring, same thing, neighboring particle with unpaired electron interacting among themselves. But what happens? They cancel the magnetic moment of each other. So net magnetic moment will be 0. So I will just write same thing. And there also, their Chi value is also positive but very small. So like like small with respect to paramagnetic also, but large for ferromagnetic it is large with respect to paramagnetic. So how they vary? So like above Tn, I will come. What is Tn? Tn is nil temperature. Chi g varies inversely proportional to T. But below Tn, Chi g decreases. This we will see. So basically, these are the transition metal oxide, mainly transition metal oxides, such as MnO2. Example. So now coming to the this. So this is Chi g versus T plot. Okay. So this is Chi g versus T plot. So there are two laws. One is the Curie law, which is said that magnetic susceptibility is inversely proportional to the temperature. So basically C by T. So this is for the paramagnetic substances. Paramagnetic substances. Right. So here C is nothing but n mu square V square by 3k. It's a constant. This is beta. Okay, it's a constant. So now if we plot like 1 by chi g versus t, you should get a linear line passing through the origin. This is for the paramagnetic behavior. But to 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 okay, to explain about the other ferromagnetic, so this we have to go for the Curie-Weiss law. Curie-Weiss law. So this said that magnetic moment chi g is nothing but c by t by theta. Okay, where theta is basically a intercept on temperature axis and it's called the Weiss constant. Okay, so this explains about the ferromagnetic. So if we see like for above nil temperature, so your antiferromagnetic we have as a paramagnetic. Above Curie temperature, which is Tc and this is Tn. Above Curie temperature, your ferromagnet behave as a paramagnetic. Paramagnetic. But below Tc, this ferromagnetism chi g abruptly rises. So that's the one thing. And for antiferromagnetic below Tn, the like basically your spin get uh, align opposite to each other and they get cancel out and their net magnetic moment will be the zero. Net magnetic moment will be zero, right? So their magnetic susceptibility will go down. So that's about all about the magnetic susceptibility versus temperature plot. Now I will just simply go to the different kinds of because in the last lecture I told you like why I will tell you why the samarium and europium are having the higher higher magnetic moment compared to the others. So the thing is that like if we discuss about the lanthanides, the lanthanides. Okay, so we discussed about the lanthanide. So the important thing is that the magnetism which is arise from 4f level. So since the 4f level is incompletely filled and it is too far from inside to be influenced by the surrounding coordinating ligand. So a trivalent your lanthanide complex function as the true ion. So suppose we have lanthanide Ln L. Sorry, this is I will just write lanthanide. Lanthanides I will give as M and ligand is L. So your MLN is just your uh, just we have like the M N plus. Okay, so this is like true ion only because your 4F label are shielded by the 5S and 5P. So it is too far from inside. That's why it's a just we have like a true ion. So if we have like a true metal ion. So now their magnetic moment is basically will come from the metal ion, which is the only spin orbit coupling. So their magnetic moment for lanthanide, your mu j is the uh, effective magnetic moment, which is well matched with your experimentally observed magnetic moment. So just I will introduce one more slide. Let's see. Okay, so I will just make one table for lanthanide and then I will go to the 3D transition metal and then this magnetic thing. So suppose this I will write heading is magnetic properties of lanthanides. So here I will write N, basically 4Fn, which is 4Fn. Here it is M3 plus. Then L, what is the L value? What is the S value? What is the ground state term? Ground state term N, sorry, and then the G value, and then mu J value, and then finally mu experimental. So we have 0, 1, 2, 3, 4, 5, 6, 7. We can go up to 14. So I will just show you some of important things. So suppose I will take cerium first. Cerium 3 plus ion. So it has L value is 3. Now how I am getting 3? Because you have this uh, F orbital, 7 F orbital 8, 4, 5, 6. 3, 4, 5, 6, 7. So here you have 0 plus 3 plus 2 plus 1 minus 1 minus 2 minus 3. So your electron filling always start from the high L value. So the L value is 3, S value is half. So what will be the ground term? So your ground term is nothing but 2S plus 1 LG. Right, so 2s plus L is 3. 3 means that is F term. 2s plus 1 is nothing but 2. And what is J? J is nothing but J is your ground state term. If I write 2s plus 1 L J. J is nothing but L plus S. L plus S is 5 by 2. Okay, 5 by 2. So why it is 5 by 2? Because S plus S to L minus S. So for less than half feet, it is L minus S. For more than half feet, it will be L plus S. So this is 5 by 2. What is the J value? J value is L plus S, which is basically your 7 by 2. Now we calculate mu J. So now I have to write a expression for mu J. What is the expression for mu J? Right. So your mu J is G J J plus 1 to power half. If we calculate this, we will get around 2.54. And your value, what is the experimental, is basically come into 3.3 to 2.5. So which is well matched with your mu J. But if you calculate your mu S value, your mu S value will come around 1.37 only, which is far deviating from this. So here for lanthanide, basically you have to calculate the uh, 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 consider the spin orbit coupling. That's the motive of like this. So I will take one more example. Like suppose I take uh, Dn is 5, like samarium. So here L value is basically 5, because if you fill the 5 electron, so 1 2 3 4 5, so it is plus 1 minus 1 cancel out, so L is 5, S is equal to 5 by 2. So what is the ground state term for L is equal to 5? The term is called H, and 2s plus 1 will be 6, and since it is less than half feet, L minus 1 will be the value. So it will be the 5 by 2, because 5 by 2 minus 5 by 2 is nothing but 5 by 2. So if we calculate the G factor, so G factor will become around 2 by 7. 2 by 7. And if we calculate the mu J, is basically nothing but sorry, this is 0.84, but we are getting the value 1.5 to 1.6. So the question is, why there is a large deviation? So to understand the large deviation, we have to see the uh, like further splitting of J. So suppose for samarium, we have J is equal to 1 by 2, we have J is equal to 7 by 2, we have J is equal to 9 by 2. So why the value is high? Because the difference between these orbital is that the difference between this orbital. So suppose if I consider um, how much the difference between this orbital is 5 lambda, where lambda value is nothing but 230 centimeter inverse. So what happens at room temperature, also at room temperature, this other orbital are also populated with this spin. So what will happen? The extra like magnetic moment will contribute. So this happen with samarium and europium. And little bit about the terbium. Okay, so that's the thing. So I will just go to the, yeah. So this professor has already written like for transition metal complexes. So if we take the ion, what is the S and L value, what is the symbol, and what is the mu S and mu L pluses. Now the thing is that for the lanthanides, we have the spin orbit coupling. But for transition metal complexes, we have the spin plus orbital magnetic moment, not the mu J. Why? Because this transition metal complexes, here ligand also affect the distribution of the electron. So that's how the mu S plus 1 will be the best to explain what is the observed magnetic moment. So I will now, this is the experimental evidence. So how we basically measure the magnetic susceptibility. There are two methods. One is the uh, covalence and other is the squid. So in covalence, you have reference sample. You just measure the weight without magnetic field, with magnetic field, and and then you measure your sample with and beam without magnetic field, and finally you use the formula to get the what is the magnetic moment. So the two thing, that magnetic field on and magnetic field off, that is the two thing you have to know. So now the from here, like from here we should ask the question why there is a need of ligand field theory. So then we have to go back and we understand what is the crystal field theory. So crystal field theory, so basically in that they basically considered that the interaction between metal and ligand is purely electrostatics, and ligand can be considered as a point charge or dipole. That they are there is the only their observation, but they didn't take account the overlap of the ligand and metal orbital. That is the reason why they are failed to explain why the C-type donor are stronger, like question like why CO is stronger ligand than Cn, or why halogen is the weak field ligand and C donor is a strong field ligand. That question we will answer through the this ligand field theory. So in ligand field theory, basically the what the ligand field theory basically uses the molecular orbitals. So it uses the MO3, and here what we have, like ligand can be viewed as a hybrid orbital, like p orbital pointing towards metal to make sigma bond. So I will briefly go how we consider each and everything. So first thing is that one of the important thing is that SAC. SALC. What is SALC is symmetry adapted linear combination. So that's the one of the important thing. So we have to uh, consider what are the available orbital on the metal, what is the available orbital in the ligand. Then we will consider what are their symmetry present for the metal and what is the symmetry present for the ligand, and then finally we see the which can be uh, overlap and give the bonding and anti-bonding, and which orbital will be the non-bonding, right? So if we have like sigma bonding, so basically they have single valence and directed towards the central metal line. So this is M. Suppose if I take the octahedral, so this is the this will basically which is the along, like which is the along the metal to ligand part. These are the sigma bond, right? But which is perpendicular to a metal to sigma bond, basically these are the pi bond. So this is the will come into the later. So here like sigma bonding interaction can happen with only dz square and dx square minus y square. That is a very important square. Sigma bonding only happen in octahedral. That is the important thing. In octahedral it can be only happen with dz square and dx square. Why? Because your ligand are coming through the x, y and z direction. So the d orbital which low points towards the uh, axis x, y, z, they only can form the sigma bonding interaction. That is the concept here. So now we will discuss about the uh, what are the uh, how we go ahead and find out the molecular orbital diagram for octahedral complexes. So first we basically consider like whatever that six ligand are there, basically each will give the two electron, and this can be six sigma donor. That is the six sigma donor to the d orbital of the metal. So they are coming along XYZ and they have sigma symmetry orbital for bonding, and anti-bonding is dz square square. Okay. So I will just briefly go to directly to the metal. These are the already available, so we can label for them. So one of the important thing is that once we take for octahedral, like in molecular term, the 6 lone pair orbital far from ligand in 6 symmetry adapted linear combination. What are the like reducible representation? What they give? So basically, they give the orbital kind of A1G, EG, and T1U. A1G is basically like S kind of thing. This is metal d orbital, and this is kind of P. So if we see that six ligand, basically they are approaching through a like octahedral. So their symmetry adapted linear combination, if we solve it, they will give the term like A1G, EG, and T1. Now we have to find out on the metal. In metal, basically you have like 3D, 4S, and 4P. 3D will be the EG, which will 3D will give T2G and EG. 4S will give the A1G, and 4P will give a T1G. So this is the like S orbital is labeled as A1G. Set of 3 orbital is T1U, and dz square and t square labeled as T2 EG. Like, so the thing is that, and this finally we have this reducible representation. I will directly go to the molecular orbital. So in this, if we see, this is your ligand after do the sac sulk, what we are getting A1G, T1U, and EG. Now in metal orbital we have 3D which are having the symmetry EG and T2G, and then we have 4S, they have symmetry A1G, and then we have 4P which has symmetry T1P. Now this EG and this EG will overlap and give the bonding and anti-bonding. That is one interaction. Then 4S A1G can interact with like A1G of this orbital and give the A1G and A1G star antibonding. And T1U from the ligand and T1U from p orbital can overlap and give the T1U and T1U star. Now the important thing is that the 6 electron from the ligand will be always down to the 12 electron will always down to the like lower to the this non-bonding electron, and your d electron will basically fill from T2G and EG. Now the important thing is that you use the CFT, right? In CFT we have 5 like orbital. During the after field ligand, it is going to the T2G and EG. That is our like um, our crystal field splitting, and this is the delta 0. Same thing we are seeing in the ligand field theory also. And you have here Dn, and basically n electron will distribute in T2G and EG. Here also we have Dn, and it will fill into the T2G and EG. So it is more or less like whatever the crystal field pattern is there, same to the crystal field theory. But the only thing is that here overlap of orbital is there. So now this gap is basically nothing but your crystal field stabilization energy, which is delta G. So whatever property balance crystal field theory explain, all the property can be explained to ligand field theory also. But the only thing is that I will come to the our next class when we have the pi orbital like CO, they have pi star anti-bonding orbital. They can interact with T2G orbital, and they can further lower this T2G orbital. Then your delta 0 can enhance. That's why they call that your CO is more stronger to the CN because of the pi antibonding arm. So those things we will discuss in the next class. So we can say that note that T2G set of orbital is non-bonding and EG is the antibonding. That is the important thing. But in crystal field theory, we haven't considered that this is the uh, bonding and this is not bonding. But ligand field theory explains that T2G is the non-bonding orbital and EG is the set of antibonding orbital. And then the important thing is that all the 6 electrons from all the 12 electrons from the ligand can be accommodated in the below the non-bonding lower to the your d orbital bonding orbital. So, and the electron from 4s and 3d of metal and the first transit will occupy in the middle portion of the diagram. This is the which is similar to what we have filled in the dn in the crystal field theory. So same thing is happening here also. That is the extended version in the ligand field theory. So the thing is that here what is the difference from crystal field theory? This is all same. This is the crystal field theory only. But here we are taking overlap of the ligand and metal orbital. That is the main. Now coming to the problem solving session. So the first question is that the point above which a antiferromagnetic system acts as a paramagnetic center is called. This is the Curie point or Curie-Weiss point, Neil point or inflection point. I will just wait for a few seconds, and if you people can answer, it's fine. Otherwise, I will explain what is that. Can you write in chat box like uh, what is the answer for the question number 1? Hello. Yes, ma'am. Tell me. Yeah, that is correct. So let me just explain that the point above which the ferromagnetic system connects as a paramagnetic center. So first I will plot the Chi versus T plot. So basically for antiferromagnetic the curve will look like this. So this is the Tn, which is called Neil temperature. Neil temperature. So what happens? This is the antiferromagnetic behavior. Antiferromagnetic behavior, and above is this is nothing but your paramagnetic behavior. Paramagnetic behavior. So what happens below a certain temperature, all the domain will be opposite to each other and they will cancel the each other magnetic moment. So net magnetic moment will be 0. Okay, so the correct answer is nil point. Similarly, like what is Curie point? Curie point is the temperature above which basically your ferromagnetic will convert into the uh, uh, paramagnetic. Now question number 2 is the for orbital contribution in magnetic moment, which is the incorrect statement. Orbital must be non-degenerate to each other. They should have the same shape. They should not contain electron of same spin, both A and C. So I will wait for a few seconds. Few people can answer that which is the correct option for the orbital contribution. This professor has discussed in the lecture number first, whatever it is. in the week 10. Okay, anyone else? Okay, but the correct option is A. So professor has told already the three rules for the orbital contribution. So first is that like label should be degenerate. Okay. So this is saying that label should be non-degenerate. That is the incorrect option. They should have the same shape. Same shape. Like suppose if we consider like T2G orbital. T2G orbital. So dxy, dyz and dzx. They can be transformed. Dxy can be transferred to dyz and dyz can transfer to zx. So they have same shape and they can transformation from one to another by just simple rotation about the axis. So suppose if we take the dxy, if you rotate with about y-axis, it will give you dyz. So that is the second criteria. Third criteria is they should not contain. This is the third criteria. They should not contain electron from same spin. So he has given that y d3 in octahedral will not contribute give the orbital contribution because you have all the three electron of same spin in the like in all the degenerate orbitals T2G3 that will not give it is violating the rule number 3 because all are in the same spin. So you will not having suppose you have T2G. So basically you have two hand up and one is empty. So this can freely transfer from one to another and give the orbital contribution. So the correct option is A. Okay. So now I will go to the next question. Transition metal halide and oxide generally shows. What is the correct answer for this? E diamagnetic, B antiferromagnetic, C ferromagnetic, and D ferrimagnetic. Can anyone just tell the answer for this question? Okay. Anyone else? That is not the correct answer. C is not the correct option. Okay. Let me. So in my once I started defining what is the diamagnetic, paramagnetic, and ferromagnetic, and then antiferromagnetic. So here your Chi value is independent to T and H. Here independent to H, but Chi is inversely proportional to 1 by T. Ferromagnetic, it is like above TC, it is this rule follow, but below TC it will rise abruptly. For antiferromagnetic, we see that above TN we have the uh, Chi will Chi will be 1 by T, but below Tn it will be like Chi will decrease drastically. So I have given example like metallic iron, suppose if you say metallic iron. Like these are the metal, the 3D metal, they belongs to the ferromagnet, but their oxides, their halides, suppose like we take Mna2, they are antiferromagnetic because in presence of magnetic field, their spins will be like their domain will be basically aligned opposite to each other, and they will cancel their magnetic moments. So all the like generally the transition metal halide and their oxide, they will be antiferromagnetic in nature. Okay, so I will go in complex, CO is stronger than Cn minus. Which theory explain this? Valence bond theory, molecular orbital theory, ligand field theory, or crystal field theory. Crystal field theory. Anyone else? That is not the correct option. Crystal field theory has not explained that CO is the stronger uh, ligand compared to the, yeah. Correct option is ligand field theory. So valence bond theory is the just a qualitative in nature. So it just says that okay, well, this will be diamagnetic or paramagnetic, this will be the ligand, this kind of ligand, this will form, this will be the shape. Basically, it's tell about the hybridization and shape. So there is no hybridization, no shape. That is the valence bond theory is tell about. Your crystal field theory, it has give the spectrochemical series. Spectrochemical series. So here that be given like CO is stronger than Cn based on the spectra. Not we have not tell about that why CO is stronger than Cn. So basically we make the complex, we take the UV visual adjustment spectra, we see that what is the delta value, and from there we say that okay, CO has higher crystal field splitting than Cn minus, that's why it's a strong field ligand than the Cn minus. But it haven't tell about why CO is stronger field ligand than the Cn minus. The theory which explained in the ligand field theory, that in next speak lecture when I will explain you like how your ligand field theory basically explain like CO is stronger field ligand and than the CMS. I will just briefly explain how. So metal has, I already told like it has T2G here, and here you have EG star. Now if ligand have pi star bonding orbital, so basically you have three pi star anti-bonding orbital. Anti-bonding. So basically, CO is basically uh, mm, sigma donor and pi acceptor kind of ligand. So what will happen? Basically, they will further split, and this will go up. So it will give T2G and T2G star. Now what will happen? This is the delta for the sigma donor, and now this is the delta prime for the pi acceptor ligand. Pi acceptor ligand. Pi acceptor ligand. So what will happen? Your delta 0 dash is always greater than delta. That is the explanation for why CO is the C, because CO is the pi accepting ligand. It will shift the T2G, which is non-bonding orbital, to further down. It will shift this to further down, and basically your gap between EG star and T2G will increase, and that's why it will give the higher crystal field speed. That's how ligand field theory explain why CO is stronger than the Cn minus. Okay, I think it will clear your doubt why this. According to the ligand field theory, non-bonding orbital are: option A is dxy dx square minus y square. Option B is dxy dxz dyz. Option C is dz square. Option D is dx square minus y square and dz square. Which is the correct option for this? So here we are basically discussing about the after complexes. So this is not written the question, but this is for the octahedral, because if we consider tetrahedral, everything will change, because their T2G orbital will be the antibond. So that's a different story, but now just focus on this. Okay, Rupali ma'am is saying that dxy, dxz and dy. Can you just write a one line why it is the non-bonding orbitals? One line can you write if I ask like specifically why you are saying that dxy, dy and dx? No, we know that the T2G orbital is there. Okay. So little bit I will explain. You people are getting, but little bit I will explain. So in octahedral field, if we apply the Salk, basically symmetry adapted linear combination, we get A1G, T1U, and EG. Right? These are the six. This is 1, 3, 2. These are the six orbital. Basically, they are coming through the X, Y, Z. So A1G is spherical in nature. T1 is the pointing along the axis. EG is the basically your, so this is S kind of orbital. This is P kind of orbital. This is dx square minus y square and dz square. Right? Now, what is happening? You have field octahedrally which is coming at the metal center. Now, what kind of orbital there on the metal center? So, in metal, we have, this is for the ligand. This is for the ligand. What is for the metal? So, for the metal, we have 3D orbital, which is if we go to the symmetry, they have T2G and EG. Then we have the 4s orbital, which are the symmetry A1G. Then we have 4p, which are in the symmetry kind of T1U. Right? Now what will happen? We have EG here also. Now we have A1G is also there, T1U, TNU also. So only which is there is a T1, T2G, which is with the non-bonding orbital. Your DXY, DYZ and DZX. Why? Because these are the orbital which lobe is in between the axis. In between the axis. So they will basically not interact with the what is the field which is approaching towards the metal line. So that's why the T2G orbital, which is dxy, dyz and dzx, will be the correct answer for this. Now next one, three set of p orbital designated by, yeah, they are not non-axial, and their lobe is like pointed in between the axis xy, yz and zx. So basically dxy will be the in between x and y, dyz will be the y and z, and dzx will be the in between z and x. Okay, three sets of p orbital designated by E1G, T1G, T2G, and T1U. Yeah. Any other opinion for p orbital?
Sir, T1U.
Yeah. So yeah, but basically, if we go to the take the help of symmetry, so basically your p orbital is degenerated at T1U. I have already told you, like 4s will be the A1G and 4G will be the T1U. Next question is the group of orbital responsible for sigma bonding formation each. Can anyone answer for this question? A is A2G, B is EG, C is T2G, and D is T1G. Anyone? Question is group of orbital responsible for sigma bonding formation each. And this is also for the octahedral. Again, if not written, please consider that this is for the octahedral complexes we are discussing about. Because if we consider for tetrahedral or square pyramid or other, it will be the completely different. Yeah, anyone else? Yeah, so you are right because for the sigma bonding, that axial orbital only contribute uh, to the bonding. So now we say that like for the octahedral we have what is the kind of symmetry E1G, T1U, and EG. So here we have to find out that which is the orbital given in the this question. So basically EG is given, which is the correct answer for this. So this is the correct answer for this question. Above the Curie point, uh, I didn't get A1G is A2G is used where? Okay, so that currently I don't know because I have just gone through the octahedral only. So if you see the other kind of geometry like square planar or tetrahedral also I don't think so it will be participating. Um, but other higher coordination number complexes, there you can see like the symmetry. Once we take the symmetry adapted linear combination, that irreducible representation should give this kind of orbital that way. But if you want, I can just read and give you the answer in the next class where we basically use the A2G and T1G. Okay, yeah. I will give the answer for like next uh, uh, class how A2G and T1G will look like. Okay, I have to go to the symmetry and then check how A2G and T1G orbital looks like. Okay. Above the Curie point, ferromagnetic sample exchange, paramagnetic, diamagnetic, ferromagnetic, or antiferromagnetic. Yeah, that is the correct answer. Like above the Curie point, the ferromagnetic sample can like act as a paramagnetic. So just I will just plot the graph. This is the chi versus T plot. So basically, it will be like initially above some temperature. This is your Tc, which is called Curie temperature. So Curie temperature. So above Tc, basically your Chi is nothing but inversely proportional to 1 by T, which is paramagnetic behavior. But below the Tc, is basically it will rise abruptly, which is the ferromagnetic behavior. So this is ferromagnetic material. Above the uh, Curie temperature, it behave like the paramagnetic. Okay. Now, how many types of orbital may be seen in the imine band of C phase? Question is like how many types of orbital may be seen in the imine band of C phase? Like, can you tell me like how you are saying the TSP and N bonding? Okay. How you are saying that D will be the correct option for this? How many types of orbital may be seen in the sun? Any explanation? Yeah, D is the correct answer that I meant. Yeah, that is the correct answer. Like it has sigma, pi, and non-bonding electron. We just show you what professor has written. So this is the basically you condense aldehyde in amine. Basically, you will get the imine, right? This is the C phase, and if you see that it is yellow to orange, solid powder. If you it is soluble in ethanol, and this absorption has. Now in UV visible spectra, so you have like C single bond N, which give you the sigma, C double bond N, that is the pi, and then it has lone pair on the nitrogen. That is basically the non-bonding orbital. So now we have first sigma, and because sigma is the stronger bond, so this sigma will be down and sigma star will be on top. After that, we will be having the pi because so I will just write. Suppose you have like right. So first one it will be the sigma star because this is the highest stabilized orbital, so antibonding will be the highest. Then you have pi, right? So it is less stabilized. So similarly, we will get the pi star. Now there is a non-bonding orbital which didn't form any bond. It will be in between the pi and pi star, which is the n star basically say or n kind of bonding orbital they say. Right. So this is the three kinds of bonding which is present in the this immune system. So I think that is the last question for this problem solving session. So yeah, if you have any doubt, you can ask me. Like in the lectures, if you anything you haven't understood properly, you can ask me and then I can explain. And from the previous lecture also, if you have any, uh,
Sir, actually, I had doubt in assignment number 3 and assignment number 4.
uh,
I told you already that.
uh, but actually currently 1 minute. I will just go to the assignment number 3 and assignment number 4. I will just open that because I think you once you said about the assignment number 3 that I know. Let me just be 3 which 3 yes. Which question like
Hmm, hmm, I think so. Hmm,
because now I also like have read long that but yeah I will try to explain it.
hmm. Aha, ambidentate ligand. So here nitro is the right answer for ambidentate ligand.
Hmm. Okay,
So
I
I
try
do
to.
same, but they mention the no right answer.
Okay, why you are saying that nitrito is ambident ligand?
Because oxygen also donation side and nitrogen also donation side, and one at a time. Otherwise, Cl is monodentate ligand,
Yeah,
oxalato is bidentate ligand, ethylene
bidentate ligand.
diamine also bidentate ligand.
Ethylene damage also, yeah, they have like only like your ethylene diamide two nitrogen donor atom, oxalato has two oxygen, chlorine is a monodentate ligand. Nitrito, okay, yeah. The important point is that here it is a nitrite too, right?
Hmm. Hmm.
So we have just I think you can go and check, otherwise I will just check, give me a second. It's already written nitrite, right? Basically
Hmm.
nitro is your imbidentate ligand because it will be the nitro n and nitro o, right? And basically your nitro o is called I think nitrite. Just I will check, give me a second. Okay, that is the I think. Yeah. So basically, if you are writing nitro, it is just telling about the nitrogen. If you are writing nitrite, is basically nitro O. So nitrito is not a ambident. Nitro is the like a ambident. It can
Okay.
be
Yeah,
nitro
but
N.
here accepted answer also they mention C, but for me that they mention wrong.
Yeah. The thing is that this question is little bit confusion. I told you already. So nitro
Yeah,
is the imbidentate ligand that I also agree. Okay. So
yeah.
basically nitro N and nitro O is the two types of
Either
the
one.
but in this option nitrito is already written. So nitrito is not
Hmm.
imbidentate ligand. That's what I think they are saying might be. But I think it should be correct option will be the C only, I think. But I don't think
Yeah,
so.
so I
Even though I
also wrote same, but they mention wrong.
Mm, okay, I think you can contact to regular TA because I'm not the TA. I haven't checked that uh, your assignment and all. Okay, but I can
Okay,
just
so
discuss. Okay. Any other
so who
question?
will
Like
check?
regular TA, you have the discussion forum here, right? Just give me a second. I will just put the. Here you have asked the question, right? In that section, you can just write
Uh,
to the question if you can. If you can write, I will just go and see. I just click on the here. So here, so many people have already asked questions, right?
okay.
Okay, so here they have also asked, suppose this Saguna has a DSR immediately when is nitrito, but you have given solution of chloride for that question.
Huh.
You for you are saying that none of the option is correct. I think there is some technical problem there. Okay, so you can just raise question here, and
Hmm.
who will be the regular TA? They should respond.
Okay.
Okay. Any other question which you have any doubt? Like,
Assignment number 4 also, but
but yeah, we can discuss like what is the correct answer. Okay.
hmm. Exhibiting linkage isomers.
Yeah. Hmm.
So here answer is D. No, no, this one is not there. I think so. The another question. Mm,
Okay.
no, actually, no. Here is no such question. Okay, I will send them the mail.
Yeah, you can
I
just
will find out.
ask the question discussion forum.
Huh.
They should reply like why they have not given that. Okay. Yeah. Thank you. I will stop the